Okay, moving on from Henry's law, where we looked at how pressure affects solubility of a gas. I'm going to move into more of a general set of properties of solutions called colligative properties. The term colligative refers to properties that depend on the relative number of solute and solvent particles in a solution and not on their identity. So the real function with colligative properties is how many particles of solute are there relative to solvent. That is what's going to determine how the physical properties of that solution change relative to a pure solution. And there are several ways in which the properties are going to change that we'll explore here over the next few videos. The first one we want to look at is called Raoult's law, and Raoult's law deals with partial pressure of a liquid. So this is vapor pressure. So if you have a pure solution, it's always got a higher vapor pressure than if you make a solution by adding a solute. So a pure liquid is going to have a higher vapor pressure than the solution that you make. So we can think about an equation there where we put the vapor pressure of the solution on one side, and it's going to be related to the vapor pressure of the pure liquid. So let me call that pure solvent here on the other side. But we know that this one's going to be higher. The vapor pressure of the pure solvent is going to be higher than the vapor pressure of the solution because solution is always lower. So what we need here is some measure of concentration that reflects, right, how many pieces of solute are there relative to how many pieces of solvent. But since these are both pressure, they're going to be measured in the same units, generally atmospheres. Could be millimeters of mercury as well. So we need a unit that describes, or a measurement of concentration that doesn't change the units in our calculation. And the measure that doesn't have units that we've talked about is mole fraction. So if we take the vapor pressure of our pure solvent and we multiply by the mole fraction of the solution in terms of the solvent, so that would be moles of solvent over total moles in the solution, right? That will show us how much the vapor pressure is going to go down. So we know mole fraction can't be more than 1, right? So for a pure material, the mole fraction would be 1. That means there'd be no change in the vapor pressure. But for every solute molecule or particle you add, the bottom of this fraction is going to go up. So the numerator is going to become less than the denominator. This value will start to go below 1. The amount it goes below 1 will give us how much the vapor pressure is going to be decreased as we make this particular solution. So the rest of the page is a couple problems kind of illustrating the relationships here. So the first problem, calculate the vapor pressure of water above a solution prepared by dissolving 32.5 grams of glycerin. We're given the molecular formula there, in 125 grams of water at 343 Kelvin. And what we're given is the vapor pressure of water at that particular temperature. Right? So we can use that in the process. Now, we know we want mole fraction here, right? If we're thinking about this equation. So we're going to want to calculate the mole fraction of this solution. We have the mass of the solute, we have the mass of the solvent. Turn those into moles and we can calculate mole fraction. So let's start with glycerin. We're going to need molar mass here, so let's start by calculating the molar mass of glycerin. There's 3 carbon atoms. We know carbon is 12.01, so 3 of them would be 36.03. We have 8 hydrogen atoms. Hydrogen is 1.01, so 8 would be 8.08. And 1 oxygen weighs 16 grams per mole. So if we add those together, 0.11, 0, carry the 2, that would be 60.11 grams per mole for glycerin. So 32.5 grams of glycerin. There's 1 mole of glycerin for every 60.11 grams of glycerin. Calculator turned off. There we go. 32.5 divided by 60.11. That would be 0.5407 moles of glycerin, our solute. Okay, and I'm keeping a few extra figures here again, although keep them all in my calculator so I don't have to round it all as I do the calculation. But I'm going to write down a few extras here just to be sure we're not introducing rounding errors. Okay, for mole fraction, we need moles of our solvent as well. So there's 125 grams of water. Now water we see all the time, so I don't think we need to go into the details of calculating the molar mass. 1 mole of water weighs 18.02 grams. That means 125 divided by 18.02. That's 6.937 moles of water in our particular sample. Okay? So we've got moles of the solute, moles of the solvent. That is enough information to put together the mole fraction of the solvent. So that would involve putting moles of solvent on top of our fraction. Whoops, 937. And then the total moles would go on the bottom. So that would be moles of the solvent plus moles of the solute. Right, the two numbers we just calculated. Right, now if we calculate that out, 6.937 divided by the sum of 6.937 and 0.5407. That would give us a mole fraction based on the solvent of 0.9277. And mole fraction, no units. I guess sol isn't a good abbreviation because that would be the same for solvent, so we write that out as solvent. Okay. There's our mole fraction. Now, if we go back to our Rayleigh law equation, right, if we've got the pure vapor pressure of the pure liquid, which we do, all we need to do is plug those two in. That'll give us the vapor pressure of the solution. So the vapor pressure of the solution is going to be equal to the vapor pressure of the pure material, which was 233.7 millimeters of mercury, times whatever the mole fraction of the solvent is. No units on mole fraction, so the pressure units will carry through here. So 233.7 times 0.9277 gives us a answer of 200, and so 3 sig figs, I'm going to round it to 217 millimeters of mercury, right? 3 sig figs from several places in the data we used for the problem. So the vapor pressure of this solution drops. It's now 217 millimeters of mercury. All right, another example using the same equation, but with some different information given and different information kind of sought for the answer. In this case, we want to calculate how much ethylene glycol, and we're given that formula, we'd need to add to 1 kilogram of ethanol, which is going to be our solvent, if we want to reduce the vapor pressure by a certain amount. So we want to reduce the vapor pressure by 10 millimeters of mercury, right? And we're given the vapor pressure of that pure solvent at that particular temperature. Okay, so in this case, if we know the vapor pressure of the pure material is 1 times 10 to the 2, that's 100. If we take that vapor pressure, 100 millimeters of mercury, and we want to lower it by 10 millimeters of mercury, that means we're looking for a vapor pressure of 90 millimeters of mercury. Okay, so that's what we're looking for in our reduced solution. Okay? Now, if the vapor pressure is 90, plug that in as the vapor pressure of the solution, along with mole fraction and the vapor pressure of the pure liquid. That means we know we're looking for a mole fraction of 0.90 to generate the change in pressure that we're looking for. So we need a solution that has a mole fraction in terms of the solvent of 0.9. Okay? So we only know one of the masses involved there, which is how much solvent there was. We can convert that into moles, and then along with what we know the value of the mole fraction needs to be, we can calculate how many moles of solute would be required. So let's take 1 kilogram there of our ethanol, so C2H5OH, and let's figure out how many moles that is. Now, watch out here, the way ethanol is written to kind of show its molecular structure. separates out those hydrogens, but we'll need to count them both in our molar mass. So 2 carbons, 6 hydrogens, and an oxygen. So 2 carbons is 24.02, 6 hydrogens 6.06, 1 oxygen is 16. 6, carry the 1. So ethanol has a molar mass of 46.08 grams per mole. So 1 mole of ethanol is 46.08 grams of ethanol. Right? And that would give us how many mole? Well, if the units canceled out, that would give us how many moles. Now I started with kilograms and I tried to cancel it with grams. That doesn't quite work. We need this factor as well. 1,000 grams in a kilogram. That would leave us with just moles. So good demonstration there of why you want to be careful with your units. If we hadn't written the units out there, I might have missed that, and then we would have gotten the wrong answer. Okay, 1,000 divided by 46.08. That means we have 21.701 moles of our solvent. Okay. Now, the only thing missing is moles of our solute. So we have to think about our definition here of how we define mole fraction. So mole fraction, we know here is 0.9. And we also know that that's going to be moles of our solvent, since for this problem we're using mole fraction based on the solvent, divided by the total moles. So total moles will be moles of the solvent plus moles of the solute. So I'm going to call moles of the solute X. Now that gives us a nice little equation. There's only one variable in there, X. We can rearrange that equation. We can figure out how many moles of the solute, the ethylene glycol, we would have needed to add for this change in pressure. So we'll start by taking the bottom of the fraction here, the denominator, and multiplying both sides by that denominator. So if I multiply 21.7 times 0.9, that gives me 19.5309. Right? And then I also need to multiply 0.9 by x, so that would be plus 0.9 times x. And that would be equal to 21.701. Right, so now I just need to kind of isolate x on one side of the equation. So I'm moving up to here. I'll subtract the 19.5309 from each side of the equation. That would give me 0.9 times x is equal to 21.701, oops, 21.701, subtract 19.5309, 2.1701 on the right side of the equation. Right, now from here to get x by itself, I just need to divide by 0.9. And x is 2.411. And again, that would be moles of our solute, which is C2H6O2, or ethylene glycol. Now, the problem actually wants the mass of ethylene glycol. So we'll have to take this quantity of moles and convert it to mass. So that, again, means we need molar mass. So 1 mole of ethylene glycol would go on the bottom. We'll have to figure out how many grams that would be on top so we can finish the problem. Now, similar formula here, there's just one more oxygen. So 2 carbons, 6 hydrogens, 2 oxygens. So 24.02 for the carbons, 6.06 for the hydrogens, 32 for 2 oxygens. Carry the 1, that would be 62.08. So if we multiply that previous answer by 62.08, that will tell us how many grams of that solute we needed to make the solution we were trying to make. Now, on my calculator, I get 149.688, and actually it keeps going. But if we look back at the problem, we're really limited to 3 sig figs from a lot of the data up there. So I can only keep the first 3 sig figs here, so I'm going to have to round that 9 up. So this is going to end up being 150. And I'm going to put the decimal in there because that 0 is a significant figure. So 150 grams of C2H6O2 is how much we would need to make that solution.